Today we'll be talking about rational exponents as a way to express roots, as another way to express roots, and then we'll also be talking about imaginary and complex numbers. So the first thing that we're going to talk about is how we can use rational exponents. And remember, rational number is just a fraction. So we can use rational exponents or fractional exponents to represent square roots. So when we've talked about these vocabulary words before. This number right here, most of the time when we talk about a square root, we don't put, this is called the index here. Most of the time when we're talking about square roots, we don't need to put an index there, but sometimes you would see if we were doing a cube root, it would have a 3 or a 4th root, or so forth. So when this index, when we have a root of some kind, we can express it as that the base, the radicand, would be the base of the exponent, or the exponential expression. So that's our base, and then the index, it's 1 over the index. Okay, so a base that is rooted, a base that is being rooted has an exponent, then it would also be the numerator of that rational expression. So for instance, if we had the nth root of x to the m, then we could also say that this could also look like this, where that m was outside to the raising the whole thing to the m. These are both equivalent, they're equal, and it would be expressed as x to the m over n. Okay, so the main idea here is that it's whatever our number under the radical is, it's raised to the whatever the exponent is over the index, okay? So again, remember the index is the number outside the root, and then the exponent would be what is raised to underneath the radical, or like I said, it could be also outside the radical. Okay, so first thing that we're going to do is we are going to look at just going back and forth from our radical form to the exponential form, and then our exponential form to the radical form. Okay, so remember, this is our index, okay, and then this would be our exponent. Okay, so it's always going to be exponent over index. So we can change this to x to the 3 over 4. Okay, and if you write the fraction sideways or up and down, it doesn't really matter. Okay, now remember, this I said, this is equivalent if I had the 5th root of b to the 3rd. It really doesn't matter where that exponent is, whether it's underneath the radical or whether the whole radical is being raised to it, it's still considered the exponent. And so we would have our base exponent over index. Okay, over here, we would have, again, there's our exponent, there's our index, 2 to the 8 over 4. And now, because that could be reduced, you usually do try to reduce that. So that would be equivalent to 2 to the 2. Okay, moving on, going the other way, when we're going to take our rational exponent, excuse me, and change it to a root form. So again, remember the number on top, this is the exponent, and then the number on the bottom is the index. Okay, so that 7 is going to be on the outside of the root, so we're taking the 7th root of x to the 3rd. All right, 27 to the 2/3, our exponent is going to be 2, and our root is going to be, or the index is 3, so it's the 3rd root of 27 squared. Okay, now sometimes you're going to see a decimal as the exponent, but we just have to figure out what is that decimal as a fraction. Okay, so 2.5 can also be 4 to the 5 over 2, because 5 over 2 is 2.5. And now we have it in a form where we can do it. Now, since this is the exponent and this is the index, since it's a square root, we don't really need to put that 2 out there, because whenever we do a root, it's considered, whenever we don't have a number out there, it is the square root. Okay, now here's how we're going to use these things. So one of the things is we're going to do is we are going to kind of simplify expressions, or simplify these bases and exponents using their powers. Okay, so the first thing that we want to do is we want to talk about kind of what are our powers of 2, 3, and 5. The reason we don't use 4 is because 4s are all considered that all be able to reduce down to powers of 2. Okay, so 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128. Okay, now our 3s, 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81, 3 to the fifth is 243, and then our powers of 5, we have 5 squared is 25, 5 to the third is 125, and 5 to the fourth is 625. All right, now what we're going to do is we're going to use these powers to kind of simplify our bases, because then if we simplify our bases into powers of these numbers, then we can kind of use our laws of exponents to reduce these and simplify them a little bit more easily. All right, so 64, we go up here and we say, okay, 64 can also be expressed as 2 to the 6th. So we are going to just substitute in for that 64. We're going to say 64 is 2 to the 6th, and then we still have it raised to the 2/3 power. Okay, now we know that when we have a power to a power, we are multiplying the exponent. So that gives us 2 to the 6th times 2/3, and 6 times 2/3, that's 6 times 2 is 12 over 3, is 2 to the 4th, and we know 2 to the 4th is 16. So that would be our final answer. All right, over here, we've got 4 to the 5 halves. Now, we can really do this kind of two ways. If we think about this and we say, okay, this is the index, we're taking the square root and then raising it to the 5th. So I could think about it as, what's the square root of 4 to the 5th? That's 2 to the 5th, which is just 32. That's one way we could do it. Now, if you I tend to go back to this kind of idea every time, is figuring out what is the simplest base that we can reduce this to. So 4, we know, is 2 squared. So we could also, again, replace that 4 with a 2 squared and then have that raised to the 5 halves power. Again, we know that when we have a power to a power, we multiply those powers. So that would be 2 to the 2 times 5 over 2. That would simplify. That would be 10 over 2, which would be 5. So again, it still simplifies to that 2 to the 5th, which is 32. So both of these are effective ways to simplify that. You'll tend to see me kind of go back to this method of simplifying whatever the base is to its lowest base to the power. All right, now we have 8 to the 5, 8 to the 5th to the 1/3. So the first thing that we're going to do is we're going to say, okay, a power to a power, we're going to multiply those powers. So we have 8 to the 5 times 1/3, which gives me 8 to the 5/3. Now, typically I would go back and I would say, okay, what could that be expressed as a power of? Well, we know that 8 is 2 to the 3rd, so we could also express this as 2 to the 3rd to the 5/3, and again, we have another power to a power, so we're going to multiply the powers. So we have 2 to the 3 times 5/3. That gives me 3 times 5 is 15 over 3 is 2 to the 5. So we have 2 to the 5, and again, we know that is 32. Now, it is, like I said, it's going to be super helpful, really, really, really helpful to memorize those powers of 2. It's going to be very helpful for you kind of moving forward. Okay, now for number 4, we have fractional exponents that are 2 of them that are added together, and then it's raised to a square. Now, we know because there's addition here, we cannot distribute that power in. We can only kind of distribute that exponent when it's all multiplication or division in there. So since we can't distribute, we're going to have to simplify each one inside. So when we have something raised to the 1/2, remember the 1/2 is another way to say just the square root of 25 plus the square root of 36, and then all of that is squared. So the square root of 25 is 5. The square root of 36 is 6. And again, we still have addition, so we can't simplify. We can't distribute that too. We have to simplify inside, order of operations. 5 plus 6 is 11. 11 squared, and that gives us 121. All right, now we have another one of those decimal exponents. And so we think about, okay, what is 3.5? What's that equivalent to? Now, remember, if you can't remember or it's not just coming to you right away, you can always use your calculator to say, okay, what is 3.5? And then remember, you hit math, enter, and it's going to give you that reduced fraction. Okay, so 3.5 is equivalent to 7 over 2. So we can now change this to 4 to the 7 over 2. And again, this is kind of, you can do it those two ways. We're taking the square root of 4 and then raising it to the 7th power. Or remember, you can also reduce this to that common base. So again, if you have square roots and the number is a square root, sometimes that's easier. You can kind of think of this as like the square root of 4 to the 7th, that's 2 to the 7th, which is 128. Or again, you can just kind of always follow that pattern of reducing this base to the to like its lowest base. Okay, so 4 is a power of 2. So 4 could be expressed as 2 squared. And then we have that raised to the 7 over 2. So we could say 7, that's 7 times 2 is 14, divided by 2 is 7. So we have 2 to the 7th, again, which is 128. Okay, so again, you can kind of think about those in those two ways. If you see that the bottom number is a 2, that's talking about the square root. And if it's a perfect square, sometimes that's just easier to think of it that way. Okay, so now we have our fractional exponent, but it's negative. Now remember what a negative exponent does. Remember, a negative exponent means it's on the wrong side of the fraction bar. So first of all, I'm going to start by trying to simplify this base of 32. Again, I know that that base of 32 can be simplified into a 2 to the 5th, so I'm going to do that first. So this can be expressed as 2 to the 5th raised to the negative 3/5. Again, when we power to a power, we multiply. So that's 2 to the 5th times negative 3/5. 5 times negative 3 is negative 15 divided by 5. So that gives me 2 to the negative 3. Now again, remember, 2 to the negative 3 does not make my answer negative. It means it moves to the other side of the fraction bar. So we can say that this is like it's over 1. Excuse me. So that can be expressed as 1 over 2 to the 3rd, which is 1 over 8. Okay, so remember, fractions, if you have a decimal, you want to change it to a reduced fraction. You can use that math enter. And then remember, negative exponents means it's got to move to the other side of the fraction bar, so it would just become a fraction, 1 over 8. Okay, so now we are going to talk about imaginary numbers. Now, I remember, as a student, I always wondered, well, what is a non-real number? You talk about, oh, no real solutions, or, and it's like, well, what is it if it's not a real solution? Well, if it's not a real solution, it can be an imaginary solution. So an imaginary number, the imaginary number, it's represented by an I, is a non-real number that is the square root of -1. So remember all those quadratic formulas, whenever we would get a negative under the root and we'd say no real solution. Now we have a tool in order to find square roots of negatives. If we have a negative under the radical, then an I is going to automatically come out. Now complex numbers are kind of integers combined with imaginary numbers. So they're usually written in the form a plus bi and are used to describe zeros of quadratic functions that have no real zeros. Okay, so a is the real part and bi is the imaginary part. Okay, now remember, let's just talk a little bit. I'm going to kind of do a little side note over here. Remember when we talked about things that quadratics that had no real roots, it was quadratics that did not cross that x-axis. Because remember, our solutions to quadratics are the x-intercepts. So when a quadratic didn't touch the x-axis, we said it had no real solution. So again, this is a way to talk about solutions to quadratics that don't cross that x-axis. Okay, so here we have the real part is 5, and then the imaginary part is 3i. You always put the real part first. Okay, so it's always real first, and then the imaginary part. Okay, that is the just kind of the format that we put complex numbers in. All right, powers of I. Okay, the powers of I go in a cycle of 4. Okay, so to simplify an imaginary number, you take whatever the exponent on I is, and you divide it by 4. Whatever the remainder is, and I'll also kind of show you if you put it in your calculator, if you don't remember kind of how to do division with remainders, you can also kind of look at what the decimal is in your calculator. So when I have I, that is the square root of -1, okay? Now, we usually just leave it as I. If we get a power of 1, I to the 1, we just usually leave it as I. But then I squared is -1 because it's like we're squaring that square root of -1. And then I to the third is -I, and I to the fourth is 1. Now, guys, this needs to be memorized. So I to the 1 is I squared -1, I to the third -I to the fourth 1. Okay, so you really do need to know that. Okay, now, when we think about this, so I'm going to look at this example. We say I to the 27. Okay, so we want to know which power is that going to like simplify it, because it's got to be one of these 4 because they repeat over and over and over after I to the 4th. Okay, so we're going to take our exponent, 27, and we divide it by 4. Okay, now I know that 4 goes into 27 6 times, right? That would be 24. And then I have a remainder 3. So I to the 27, I don't care how many times it goes in. This is the only part I really care about. So what is that remainder? Our remainder is the 3. So I to the 27 is the same as I to the 3, which is just -I. Okay, now let's say that you are like, I do not really remember division, with remainders. Then the other way you could do this is say, okay, I'm going to plug in, I'm going to just take my calculator, and I'm going to take 27 divided by 4. Okay, notice that I have a 0.75, right? Because it goes in there 6 times, and then it has that 0.75. Okay, now whatever that decimal is, these can kind of correspond that way as well. Okay, so if it has, when you do it in your calculator, if it has a 0.25, then that really is like a remainder of 1 because it's like 1/4. Okay, if it has a 0.5 at the end, that's an I squared. And then if it has a 0.75, that's an I to the third. Now, if it doesn't have any decimal, then that means that 4 goes in evenly, and it's just the number 1. All right, now the other thing that you're going to need to know is about a complex conjugate. So if we have a number, a complex number, a plus bi, then the complex number a minus bi is the complex conjugate, okay? Notice to find the complex conjugate, you keep the real number the same. Nothing about the real number, the a, changed, but you change the sign of the imaginary part. Okay, so you will need complex conjugates when you simplify fractions with complex numbers. Okay, so we have this number up here, 5 plus 3i, so the complex conjugate would be 5 minus 3i. Again, notice the 5, the real part didn't change, but I changed the sign on the imaginary part. All right, so now let's do some simplifying of these. Oh, this is a typo. This should not have been, let's see, what is that supposed to be? So, sorry, we're going to take that out. That negative shouldn't be there. It should just be 2 root negative 45. We'll get to that one in a second. Okay, so now previously when we had square roots of negatives, we said, oh, well, there's no solution. Now we can say, all right, well, this under here, so we could say this part under the radical, we'd have that 3 on the outside, and that could be split into 9 and negative 1. Well, we know that the square root of 9 is 3, so we have the 3 on the outside, times the square root of 9, which is coming out, that's 3. And now we know that the square root of the negative 1 is I, so 3 square root of negative 9 can simplify to 9I. All right, so again, there wasn't supposed to be that negative there, so it should be 2 square root negative 45. All right, now we simplify this the same way we would normally do. We just know that an I is coming out because there's a negative under there. So we think about, okay, what perfect squares go into 45? Well, we know that that is a 9 and a 5, and that square root of 9 would be 3. So we have 2 times the square root of 9, that's 3. Because there's a negative under there, we know an I is going to come out. And then that 5 did not have it's not a perfect square, so it's going to stay under the radical. So then I have 2 times 3i, that is 6i, and then that root 5 just stays under the radical. So again, I look and I say, okay, what are perfect square factors of 54? Sorry, I keep giving us 9s. We know that this is 9 and 6. So 9 is a perfect square. 6 is not. There are no other perfect squares in there. So we have our negative 1/3 that's already out there. We take this, multiply that by what's coming out. So the square root of 9 is 3. Because there's a negative under there, an I is going to come out. And then that 6 had nothing else to simplify with, so it's going to stay in there. So then I have negative 1/3 times 3i. Well, those 3's are going to cancel out, so I'm going to have negative I root 6. All right, so now we're going to practice simplifying the powers of I. So I have I to the 23rd. Okay, so every single time you're going to take that 23, whatever that exponent is, and divide it by 4. So when I put that in my calculator, I get 5.75. So that 0.75, that reminds me, I go up here and remember, okay, 0.75 means that there was a remainder of 3. So then this, I to the 23rd, is the same as I to the 3rd, which is just negative I. All right, same thing. I'm going to take the exponent, divide it by 4. When I do that, I get 8. So that means there was no remainder, okay? So that means it divided evenly by 4. So I to the 32 is equivalent to I to the 4, and that, from our chart up here, is just 1. All right, exponent 101 divided by 4. When I do that, I get 25.25. Okay, so that 0.25, that means there was like 1/4 left, or a remainder of 1. So I to the 101 is equivalent to I to the 1. And remember, when it's I, we just leave it as I. We know I is the square root of negative 1, but we can just leave it as I. All right, finding the complex conjugate. Now remember, the complex conjugate leaves our real number alone and changes the sign on the imaginary part. So our real number is 9. This is a negative, so we're going to change that sign and make it positive. I. That's it. That's all I have to do. All right. Now, this number, this complex number does not have a real part. It only has the imaginary part. So the only way to change that is to change the sign. So it would just be positive for I. Okay, now this one's a little confusing because is it in the right order if we can think that our order of our complex numbers should be a plus bi, this one needs to be flip-flopped in the order. So really, the complex number would be root 3 plus I. So then that means my complex conjugate, we leave the root alone. It does not change. And then this was a positive, so that means my conjugate needs a negative. All right, and then we can do operations with complex numbers, just like we do operations kind of with anything. You want to think about these as like terms. You're going to combine real numbers with real numbers and imaginary numbers with imaginary numbers. So I notice when I have subtraction, that negative is going to need to distribute into that second parenthesis. So I would have 14 minus 2i minus 23 minus 6i. So we treat these like terms. So 14 minus 23, that's negative 9. And then negative 2i and negative 6i, that would be negative 8i. Now remember, when you're combining or when you're giving me an answer that's a complex number, you always want to put the real part first and the imaginary part second. Now here, these complex numbers are added. Okay, so remember, if they're added, I don't need to change that back parenthesis. So I just have 3 plus 2i plus 7 minus 4i. So again, like numbers, 3 and 7, that gives me 10. Pardon me. And then 2i, negative 4i gives me negative 2i. Okay, we can multiply with complex numbers, which just means here we have a coefficient out front of a binomial. So that means we just need to distribute that 3i. So 3i times 2 is 6i. 3i times negative 2i is negative 6i squared. Okay, now an I squared is something that we always have to pay attention to. You should never leave an I squared in your answer because we know from up here that an I squared is just negative 1. So anytime I see an I squared, I usually kind of circle it and I put a line through it because what that's reminding me to do is that this is saying that 6 times negative 1. So then really all that I squared does is change the sign in front of it. Okay, so this would be 6i plus 6. And then again, because we're supposed to give our answers, we need to give it in the a plus bi form. We're going to change the order. So our real number goes first, 6, and then we have our 6i at the end. Okay, so what you'll usually see me doing from moving forward, anytime I have an I squared, I usually just will cross it out and change the sign in front of it. That's kind of the way, my notation to kind of remember that that's what I'm doing. All right, when I have a binomial squared, remember I can't, this isn't just 4 plus 9i squared. Remember I have to FOIL that. So I write it twice, and then I do my first, outer, inner, last. 2 times 2 is 4. Outer, 2 times 3i is 6i. 3i times 2, that's another 6i. And then 3i times 3i is 9i squared. Okay, so I see this I squared, I circle it and I mark it out. Now that's going to change the sign in front of it, so this positive is going to become a negative. So now I have 4 minus 9, that's negative 5, and 6i plus 6i is plus 12i. All right, now here when we have fractions, when we're dividing with complex numbers, we kind of think about this similarly to how we think about radicals. Remember, we could never leave a radical in the denominator. Same thing here. We cannot leave a complex number in the denominator of a fraction. Okay, so the way we get rid of this is kind of why we talked about that complex conjugate. So the way that you get rid of a 1 plus 2i is to multiply it by its conjugate, 1 plus 2i. I'm sorry, I said 1 minus 2i. We're going to multiply it by 1 plus 2i. Whatever I do to the denominator, I have to do to the numerator. Okay, and now we're going to FOIL. Now the reason that we do it by the conjugate is because these are kind of like those difference of square factors, right? So that inner part where we're going to have the I terms, they go away. And then when we get the I squared, we know we can just change that and make the sign the opposite sign in the denominator. All right, so we're going to FOIL both the numerator and the denominator. Okay, so 2 times 1 is 2. 2 times 2i is 4i. 3i times 1 is plus 3i. And then 3i times 2i is plus 6i squared. Now, a c and I squared, I'm going to cross it out, and I'm going to make that a negative in front of it. So change that positive to a negative. All right, now we do the denominator. 1 times 1 is 1. My outer is plus 2i. My inner is minus 2i. Okay, so you see that those go away. And then I have negative 2i times positive 2i. That's negative 4i squared. Again, I see that I squared, so I cross it out and change the sign in front of it. Now I'm going to just combine my like terms in the numerator. 2 and negative 6 is negative 4. 4i and 3i is plus 7i. Down in the denominator, we saw that 2i and negative 2i canceled out, so I just have 1 plus 4 is 5. So notice there is no imaginary part in our denominator, and we will have an imaginary part in the numerator. That's okay. Okay, but we just cannot have an I in the denominator. Okay, so our last example, we need to get rid of that complex number in the denominator. So we come down here. We don't change the real part, so it's negative 5, but we change the sign of the imaginary part. So minus 4i, whatever we do to the denominator, we have to do to the numerator. And then, again, we FOIL. Negative 4 times negative 5 is positive 20. Negative 4 times negative 4i is positive 16i. Negative 3i and negative 5 is positive 15i. And negative 3 and negative 3i and negative 4i is positive 12i squared. Again, c and I squared, cross it out, change that to a minus. All right, now my denominator. Negative 5 times negative 5, positive 25. My outer is going to be plus 20i. My inner is going to be minus 20i. So again, those cancel out just like they're supposed to. And then I have a negative 16i squared. See that I squared, cross it out, change the sign in front of it. So again, combine my like terms. 20 minus 12 is 8. 16i plus 15i is 31i over, again, we saw those I terms canceled out like they were supposed to, and then 25 plus 16 is 41. Okay, so that wraps up our lesson on complex numbers and rational exponents.